All right, so this mini lecture is going to look at some basic concepts of simple harmonic motion. Now, what do we mean by simple harmonic motion? That is simply telling us the behavior of a particle, its motion, that is showing some periodic behavior, some consistent behavior. So, like a pendulum swinging back and forth, like a child's toy that hangs on a spring that bobs up and down in sort of a periodic wave-like fashion. We're going to look at this type of motion and how we analyze that type of motion. What kind of information can we get out of that type of motion? All right, so in this mini lecture, we're just going to define a few variables that we use to describe a simple harmonic motion. And then in other lectures, we'll talk about how we use the math and what do we do to solve problems in simple harmonic motion. So when we think about periodic motion, let's imagine for just a second. We'll start with a child's toy, and it's hanging on a spring. And so there's the toy hanging on the spring. And if I tap the bottom of it, we see that that kind of bounces up and down. So we know that the object bounces up, the spring gets a little shorter, and it bounces down, the spring gets a little longer, and it kind of goes back and forth through this motion. I think you can maybe imagine that, all sort of oscillating around this sort of middle point. If we're going to describe that motion, we can talk about how many oscillations it's doing in a certain amount of time. So when we talk about the number of oscillations, the cycle up, then down, then back up, in a given amount of time, we call that the frequency of the motion. So the frequency is the number of oscillations, the number of oscillations or cycles in a given amount of time. Now, we often use that time base of seconds, so we talk about the frequency as the cycles per second, and that has a unit of a hertz. So if we examine the behavior of this child's toy bouncing up and down, and we see that it goes 30 cycles in 10 seconds. So if we have 30 cycles, it goes up and down 30 times in 10 seconds. We can calculate the frequency of that motion as 30 cycles in 10 seconds, or 3 hertz. So the number of cycles per second. All right, so that's frequency. We can also describe how long it takes for it to do a single cycle. So I can talk about cycles in a certain amount of time, or I could say, well, how long does it take to go up, down, and back up? What is the time it takes to complete one cycle? We call that the period. So the period is the time of one cycle. So if I watch this bobbing toy and it goes up and then down and then back up, that's one cycle. It takes 3 seconds to do that. So one cycle takes 3 seconds. We would say that period then, and we use this capital tau for the period, is equal to 3 seconds. Now you might quickly recognize that, well, if the period is the time it takes for one cycle, and the frequency is the number of cycles it takes per time, these two must somehow be related. And they are. These two quantities that they both sort of describe the same thing. They're related through the mathematical equation that the frequency is equal to 1 over the period. So this is going to be an important thing for us to keep in mind as we look at simple harmonic motion. We can describe either the frequency or the period, and those two are related to each other. We can get one from the other. All right, well, what else might we be interested in terms of this behavior? Well, we might be interested in how far it travels, how high it goes, what we call the amplitude. Now, the amplitude is very important to recognize that it's not how high it goes one to how high it goes to the other, but if we recognize this equilibrium position, if I just hang my mass on that spring and it kind of settles there due to equilibrium forces, right? The upward restoring force is equal to the downward gravitational force. The amplitude is how far it deviates from that equilibrium position. All right, so the amplitude of the motion is how far from equilibrium. So I might pull that child's toy down really far and it'll bounce up and down in really big periodic motion. Or I might just tap it a little bit and might bounce up and down in very small periodic motion. So the amplitude kind of gives us a sense of how large that motion looks from a displacement standpoint. And we want to keep in mind that the amplitude is how far from the equilibrium position. All right, so 3 different things we want to think about, 3 pieces of vocabulary to describe our simple harmonic motion. The frequency, the number of cycles per second, the period, the time of one cycle, and the amplitude, how far from that periodic motion. How far from that equilibrium position. Now we're going to use these ideas to mathematically describe the simple harmonic motion behavior. And we can use these ideas to describe an equation that gives us information about the motion of an object in simple harmonic motion. But I also want to show you, and we'll get to that, I think you'll be able to see it if we look at how does this behavior look if I were to kind of plot it graphically, and then can we get a sense of what that mathematical relationship is for simple harmonic motion. All right, my board's not erasing very well today. Okay, so if I were going to sort of examine how this motion looks like, this spring going up and down and up and down, in order to plot the position of that spring, or that mass at the end of the spring, I should say, as a function of time, and I start it going at, it starts at that equilibrium position, and I kind of start it going upwards, we would notice that it goes up, kind of hits a maximum, kind of comes back down, hits a low maximum, it goes back up, back down, back up, back down, in a wave-like pattern, periodic motion. So this distance it travels from equilibrium to its peak, that again is that amplitude. How long it takes to complete one cycle? This amount of time is the period. So we can get some information off a graphical representation of the motion as we look at its position versus time behavior. And of course we could get the frequency by taking 1 over the period. This looks hopefully familiar to you when we think back to our trigonometry. This is our representing the cosine. And we actually represent simple harmonic motion as a cosine function. It's equal to the amplitude times the cosine of, in a cosine function, is how much time it takes, right, for a cycle to complete. This is, we call this the angular frequency times the time. And actually, it's possible that I kind of phase shift this, that I could start my cycle maybe when it's already moving. In the work that we do, we are not going to worry too much about the phase shift, but I want you to recognize that base, that we can always shift our sine and cosine waves. In this case, we're representing that motion, that position as a cosine. We can always shift them a little bit in time through that phase. So let's again just define some of these things. The A represents our amplitude. This represents our angular frequency, how often we're making those cycles, defines how many cycles happen in a certain amount of time. T, of course, is the time we're interested in. And that phi is our phase shift, which again, we're not going to see very often for our purposes. Now, because this is an angular frequency is actually related to the frequency I was talking about before. Through our polar coordinates, the angular frequency, omega, is equal to 2 pi times the frequency, the cycles per second of our wave. So what we often see written is times our time. This relationship for position for simple harmonic motion. Now you know that if I have position information as a function of time, I can get velocity information as a function of time, because we know that the velocity is simply the derivative of our position with respect to time. So not only can I describe the position of the simple harmonic motion, but I can also describe how fast that object is moving at any point in time. And so we can use our understanding that the derivative of the position gives us velocity. We can also look at the acceleration. How's that object accelerating? Because we know the derivative of the velocity gives us the acceleration. When we do that, we find that, especially with velocity, we find that our velocity as a function of time is 2 pi times the frequency times the amplitude. And if we take the derivative, of course, of a cosine, we end up with that sine 2 pi f times t. What does this tell us? This tells us that the velocity is also periodic, and it also gives us some information, because when I am at a point where I am at a peak velocity, right, my highest slopes, the maximum velocity in my periodic motion is equal to, when the sine is equal to 1, is equal to 2 times pi times the frequency times the amplitude. So this is also really great information to use as we use this equation of motion to define some of the behaviors of objects experiencing simple harmonic motion. All right, lots of information in terms of some base knowledge for simple harmonic motion. We'll do a sample problem just really with frequencies and amplitudes. I wanted you to start to recognize how the equations, how our behavior dictates, shows. We can model it through this equation of simple harmonic motion with a cosine function. And again, reminding ourselves that the frequency is our cycles per second, in case you just want to screenshot this last bit, and our period is the time for one cycle. So these are our important details. Our amplitude is from equilibrium to our peak. All right, good job.